So we're live. I'll go ahead and pop out the chat and keep that just in case someone joins. Otherwise, we will chill here for a few minutes. I went ahead and did all the notebooks in Google Colab this time, mostly because we were having some issues with Colab, or with GitHub. So go ahead and wait a few more minutes, and then we'll get started. All right, well, it's close enough the time, so we can go ahead and get started. So this will be the last lecture for the tabular module. And I know initially I said I was going to do TabNet, Deep GBM, and Time Series, but we're just going to do TabNet and Time Series, mostly because I still had a few little headaches with moving and whatnot. But I'm going to try and get Deep GBM implemented here in the next few weeks, hopefully. If not, after we finish the text module. But in the meantime, let's talk about TabNet. So the notebooks for today are 04 TabNet and 04 Time Series. And TabNet was a paper that came out a little while ago. I want to say early-ish last year. Let's go take a look. About, well, it was last updated in February of this year, but it came out a little before that. And the difference between TabNet and, say, our fully connected models is it utilizes attention, and and attention-based model, we can understand what's going on. It has, attention. We can look and see how it looked at each particular input and how the model behaved based upon it, which we can sort of emulate with, with permutation importance and stuff like that we looked at last week. But here it's directly ported. Now, I'm not going to show the attention part quite yet. I'm working with Michael Grankin on bringing that fully together. He developed a wrapper for TabNet's model itself, the original implementation in PyTorch. So expect to hear more about that in the next few weeks. But for our quick example, we're going to use Mikhail's fast TabNet. We're also going to utilize the fast dot library to sort of visualize what's really going on with these models and where they sort of differ. So first, we're just going to build a very quick adults data set. So, your path, your data frame, cat cont names, splits, same thing that we've been working with for the last few weeks. Now, the bit I want us to focus on is how the batches are actually fed into the model. So here I have a batch size of 1, so we can just directly look at one particular input. And let's see what our model is getting. So if we look, we have our categoricals here, so they're one-hot encoded. Or sorry, they are encoded, not one-hot. And then we have our continuous variables here normalized. And then we have the categorical input, that's 0 or 1. So most models instead want a continuous input of our categorical and continuous features. And so specifically with tabular models and fast AIs, that sort of happens after the embeddings. And so when we look at implementing TabNet, where you should bring in custom models to where they accept this sort of input. So we're going to try and visualize our tabular learner, so our basic learner, with that 200, 100 layer size, with the fast library. Now this is a more or less visualization wrapper of sorts that Jeremy and Sylvain worked on running on top of PyDot, which runs on top of GraphViz. So now instead of fastai, where it's just on top of PyTorch, we have a whole chain of effects. But let's see what we can do. So I've hidden the code here because it's kind of messy. You can try and follow along and see sort of what's going on here, but here is a basic rundown of our model, right? So we have our preprocessed input that feeds to an embedding matrix, that's categorical, otherwise a batch normalization layer, and then our 3 fully connected lin batch norm drop layers, essentially, where we have, a batch norm, dropout, a linear, followed by an activation function, unless we're on this last one, in which case we just get the output from the linear. So this is the fast AI model in a sum up. It's not very big. We only have about 3 fully connected layers, along with, an embedding matrix and batch norm, so nothing big. Now, how does that compare to TabNet? TabNet's a very deep model. So if we I'm going to hide the chat here for a moment. Look, this is the entire model in a sum up. So we still pre-process the input. This is what I was talking about, where we're going to follow the same initial steps. So we're going to pass everything through our embedding matrix and drop out. That's categorical, pass the continuous through batch norm, and then we concatenate those values and then feed them through what is essentially TabNet, which has 2 transformers followed by a final mapping. And that's an attention transformer, a feature transformer, and then we get 4 outputs from it. Now, why those 4 outputs matter is TabNet operates by putting a mask, essentially, over each value as it's passed in. And so with that mask, we can sort of see and adjust how each of the values were affected, more or less. And so that's why we have these masks, mask explain, mask loss, followed by our actual output. Now, the main implementation we're going to be looking at, we just care about the output for right now because we don't have explainability yet in a way that's seamless for our implementation of this. So this was something I was kind of hoping to get done beforehand, but that's okay. We'll get it done later, and I will obviously update you guys with those results. But let's take a look at these transformers, because transformers, they are certainly in the news in terms of NLP. So the feature transformer isn't too much per se. You can see that we have these two linear layers followed by what's called a glue block. And the glue block, you can read about it in the paper, but essentially think of them almost as mini trees in some ways. And so these glue blocks are what allow us to sort of take our attention matrix and its output and then put it into something that we can more or less feed through that last linear layer and grab our outputs. And then the attention transformer is really the bricks and bones when it comes to model interpretability with this. So we start with the linear layer, go into what's called ghost batch norm, which is a completely different paper, which I'll link to after the lecture. And then when we send everything to the model, we'll actually keep the previous input. And so that's where the attention comes into play. We do a torch multiplication of our current input as it's being fed through the model, along with the prior where it was before, and then we do a sparse max activation on it. So this sort of combination is what lets them do this attention, more or less. And along with that, we can sort of call the attention transformer the encoder and the feature transformer our decoder, because we're familiar with those terms now. And then, this is just pre-processing the input in a way. So now that we kind of know what this model does, let's sort of look into how we fit that into the framework. So I'll start off just by saying that in my experiments, I've had mixed results with TabNet. This is taken from a separate repo rather than Mikhail's in terms of updating. So as they sort of update the implementation, you might notice it start to get a little better because it's more closer to what the original paper wanted. I believe the original paper was in TensorFlow. And so that was something I definitely noticed because I looked at this last a few months ago. But when I was messing around with it, it took a long time for me to get the same number or the same accuracy as fastai does. But when I was running adults, I didn't see that behavior. So that's definitely something to play around with as sort of a forewarning. But before anything else, most of these models are going to want our embedding sizes. And so we'll just simply, grab them, get embedding size. This is a fastai function, pass in our tabular pandas object, and we'll get back this sort of more or less dictionary of sorts with our embedding matrix, with our size of our embeddings. Now, for the TabNet model itself, there's a lot of hyperparameters that you can mess with. You have ND, which is our prediction layer, its dimensions, NA, which is the number of dimensions in the attention layer, the number of steps that you can perform, a scaling factor for attention, momentum, which this is batch norm. You can run this in your regular fit1 cycle. I believe that we adjust for that. The number of independent glue layers in each block. So those are those, GLU block number of layers in our glue blocks here. Now that's normally 2, which we're going to keep. And then and shared is the number of shared glue layers in each block. So essentially what that means is they share the outputs and then concatenate them together more or less. And then epsilon is just a hyperparameter that should be kept as low as possible without it being log 0. Now we're going to attempt to build this model more or less with TabNet. So that's going to be a dimension of the prediction layers of 8, attention dimensions of 32, and roughly 4 steps. Now, the first thing I want to show here is how we can incorporate TabNet using fastai code. So this would be for any sort of tabular model, more or less, that expects the input after it's been run through an embedding matrix. So all of this right here is fastai code. And all of this here is fastai code. That's the fastai model. And so all that that's doing is running my input through the embeddings and through the batch norm. And then from there, I can simply, use TabNet no embeddings because we're already pre-calculating our embeddings and just pass that X in. And this will be the same for most any model that expects its input after it's been passed, through the embedding layers. If it has custom embeddings in the model's functions, then go ahead and take them out because we can pre-compute them with fastai's embedding rules and just worry about them ourselves because we have the code. It's easy to use. Now from there, you'll notice I have this attention equals true or false. So this is just the precursor of the attention. Anytime that I call an instance of the model, we're calling its .forward method. And so I can do this right here and it won't affect training because I've set a default value of attention. Because remember, each time we grab a batch, we have our categorical and our continuous. And then I can simply say, once the attention module is ready, if true, whenever I build my function, it'll go ahead and get my X, the mask loss, the masks explain, and the masks. But we don't care about that here. We just care about training. And so we're just going to ignore these other 3 values. And so we just simply pass that into the forward, check to make sure if there's a Y range or not, which this is also fastai code. And then we return it. And that's essentially how you can bring any sort of tabular model into the framework well and with minimal ease. But other people's code aren't necessarily clean, and so it might take a little bit of work around just understanding first their code before you can port it in. But the less amount of their code that you have to rewrite, the better. So keep an eye on that whenever you're wanting to do custom implementations. Now, the last bit we need to do is, remember we currently have a batch size of 1 right now. So we're going to rebuild our data loaders to a batch size of 1024. Something decently large that we can push onto the memory. We'll build a TabNet model with our embedding sizes, our number of continuous names, the total amount of outputs we're expecting, so our classes here are 2, and then that ND and A followed by the number of steps. Now here I just have 1. I don't have 4, but that's okay. And then as this is a tabular model and we're assuming that we're not going to be training per se as long, I went ahead and used the Ranger optimizer because it should help with that. So we'll just build a learner with data loaders, our model, the loss function. We'll obviously keep the same metrics of accuracy and our custom optimizer. Now the one thing you'll notice here is that's a very, very steep LR find. We're not used to it being that steep, and that's okay. Don't let that scare you. I went ahead and trained with 1e-1. That's okay. It recommended 2.7, so like somewhere around here-ish. And so you can go ahead and do that. Learning rate, the learning rate finder is really an art rather than a science. And so you kind of just pick based off the curve to roughly the right amount. And then if you want to get close to, we have our suggested learning rates. But now I'm going to do a fit flat cosine for about 5 epochs. We can see that we got about 83.6% accuracy, and it doesn't take very long to train at all in terms of speed. And so that is something very nice, where if we're trying to train for many, many epochs because I've had a few instances where I've trained it for, a couple hundred epochs. Because the longer you train it, the better the algorithm is. It's a very easy algorithm to train, just it sometimes will take a long time. In the original paper, they trained for something like 400 and 600 epochs when they were originally training. The one cycle policy and fit flat cosine can help with that, but um, besides this particular instance, it usually takes me 20, 30, 40 epochs to get something competitive. So just keep that in mind that it is going to be a little longer in terms of training and different compared to our regular models that we're used to. The code is here for you essentially to play around with. It's a different tabular model, and once we get attention working, this will be something extremely useful for people that need that interpretability aspect greater than just the sort of peek in that other methods can give us, like our normal linear layers and whatnot. But from there, are there any questions over TabNet? If you're curious about the exact architecture, there's a link to the paper in here, so you can go read about that. But any general questions real quick? All right, if not, and I'll keep an eye on the chat, then we'll go ahead and visit the time series module. Now this might be a little bit shorter of a lecture, and I'm sorry about that, but I wanted to have more material prepared. Good, we'll live. And then of course, if you have any questions, feel free to just ping me. But from there, let's go into time series. So the particular submodule we're going to be working with is Time Series AI2 by Ignacio. And there's a humongous mega thread on time series in the forums. And the general goal of time series is to use data with more or less any number of dimensions. And so what that means is instead of just a single dimension like our regular tabular, where we have one particular input for one particular segment in time, or say images where we have 3 channels RGB, we can have any number of particular time steps with any number of variables, essentially. So instead of just having one line where, say, maybe we try and do a time step by having multiple instances in one go, we can just pass this into essentially what transforms it into something like a convolutional layer. So the first bit we need is to install the GitHub version because it's not available on PyPy yet because it's still in development. But this is what our inputs are going to need to be. And inside this library, Ignacio has let us be able to grab any UCR repository that's more or less there for univariate and multivariate data sets. Now, if we go look at the UCR database, you can see that there's a whole lot of them in here. And I'll link this in the chat, but essentially you can look at the paper, the number of classes, the size of the training and test, the time series length, so that's how many instances of each input there are, followed by anything else that you could possibly care about with your data. Now we're going to care about the starlight curves dataset, and I just chose that one because it was a good example and it's what Ignacio uses. So we can grab our training x's and y's and our valid x's and y's by calling getUCRDataset, pass in a name for the data set that we care about, and then I chose verbose as true and on disk as true because one thing that Ignacio has kind of figured out is how to utilize numpy arrays that are stored onto your disk. And so all of the data is not stored in memory. Instead, it's called from a memory location to go and open a spot on your disk, which can save on overall, computation head quite a bit, or on overall memory load. Sorry. So here we can see that we have a very small training data set of about 1,000 instances, and we have a very large validation set of 8,000 instances. So it's a very interesting problem. Now, as the data is already split between train and valid, we're going to concatenate them because we can figure out what index that was. That's everything after 1,000. And then we'll go ahead and save the numpy arrays away. And then we can load them back in via this memmap. And what that allows us to do is read the data directly from memory without having to actually open the files per se. So now that we have that out of the way, we can go ahead and just make our splits. This will just recreate the same environment we had with the x train, x valid, y train, y valid. And now when we're using this library, it expects a three-dimensional tensor array where we have the number of samples first in the first dimension, our number of variables and our regular variables in the second dimension, and then how many time steps essentially as the third dimension. So let's take a look at what that even looks like. So there's a special time series tensor essentially to work with this particular data type. And so if we just pass in our x here, we'll get a time series tensor that tells us we have 9,200 samples with one variable, and each time length is 124 samples essentially. Now disregard that, that's for a different data set. Now, one thing that's very nice is we can use that directly in the high-level data block API with a time series tensor block. And the time series tensor block already has all the transforms in place that you need, so we don't even have to call any item transforms or batch transforms. We simply have to make our splitter, make some getters, which all this is saying is from my inputs, the first one will be an x, and the second one will be my y's. And we can do that because our inputs are a bunch of numpy arrays. And then we call the data block with just our blocks, our getters, and our splitters, and that's it. Now, the last bit we need to do is actually zip together our x's and our y's, and so that's what this itemify function does, and this is another one from his repository. And now we can simply just make our data loaders. And if we look at a batch of data, it looks like a bunch of graphs, which makes sense because it's over instances of time, and if we remember, each one has a length of 1,024. There's 1,024, so we have 1,024 different instances in one particular segment. And if we're unsure about if the data is still on the disk, we can go look at the data loaders dataset and see the memmap. Now for training the actual model, the one we're using is called Inception Time. I've linked a Medium article discussing it, but it's more or less a very, very good, if not state-of-the-art, time series model. And all we need to do to utilize it is pass in the number of input classes and the number of variables. So here we look, our expected classes is 3, and then to get the input variables, we take the shape in the second, the negative second dimension. And so if we remember, that's our middle dimension that tells us how many variables there are. So if we look here, that's right here. Because remember, in our case, it goes batch, length, variables, samples. More or less. That's what each input's going to wind up being. And so if we grab our input variables, we see that it's 1. And then we go ahead and make an inception time model by passing that in. And then just like everything else, we go ahead and pass in the data loaders, model, the loss function of cross entropy, our metrics, and in my case, I chose to, again, use the ranger optimization function. Now we can call in LR fine, and this is something a little bit more familiar to what we're used to. So I just went ahead and went with the suggested LR minimum, which was about 1e-2.5. And so I fit for about, 10 epochs. And it looks a little unstable, but you have to remember that we're training on a data set where we have 1,000 samples and we're extrapolating it on like 4,000 other samples or so, if I recall correctly, right? Because that was inputs of 8,000, sorry, even more than that. And the nice thing is this works with any sort of time series data that you have. It can be multivariate, it can be univariate, and puts it in a nice building block way in the high-level API that makes it really, really easy to use. And so I was very impressed by this. I got it set up in just a few minutes by following his tutorial notebook, which I will also link to that notebook, which is linked right here. But that's about it. I know it was a much shorter lecture. I think it was only like 20 minutes or so, 30 minutes. But if there's any questions, please let me know while I'm here. Otherwise, next week, we're going to get started on natural language processing and sort of exploring the depths of it. What is, the LSTM, looking a little bit at IMDb. Also, the amount of time to train our models is going to increase, not exponentially, but yeah, I'd say exponentially. So if you want to sort of follow along or run these notebooks on your own, while Colab can work nice, even with Pro, I believe it still times out in something like 24 hours. And depending on the language model, it might take longer than that. I'm going to be showing examples of training those models, but the code that we're going to be running is going to be a very small subset of that. And so the results can fluctuate. But besides that, thank you guys for joining me today. Please do stay safe out there. And I will see you all next week. Feel free to post in the mega thread if there are any questions. Thank you for joining.